Hello, my name is Gabriel Eckstein, and I'm the president of the International Water Resources Association. On behalf of IWRA, I want to welcome you to this important session, A Hidden Treasure, Groundwater as a Tool for Climate Adaptation and Resilience. I'm especially excited about this program because of my own personal and professional interests in groundwater resources, to which I've devoted much of my academic career. Groundwater is a critical global resource, and it is a critical component of the climate change puzzle, and a tool that will help communities and nations expand their capacity to adapt to the changes occurring around us and to become more resilient in the face of uncertainty. From hydrogeology to groundwater for human and environmental health to groundwater governance, IWRA and its partner organizations here today are committed to improving understanding of this critical resource and to ensuring that it is recognized as an important tool for water resiliency to whose sustainable management must be prioritized. We at IWRA look forward to expanding the role of groundwater in the climate change agenda and to 2022, when the global focus will turn to groundwater under the UN theme of groundwater, making the invisible visible. Thank you to all of you for attending in person and online. We sincerely hope that all of you become champions of groundwater as a vital resource for climate change resilience and adaptation.
Distinguished organizers of the COP26 Water Pavilion and this special event, distinguished delegates, ladies and gentlemen, I'm honored to give these welcome remarks on behalf of the Secretariat of the African Ministers' Council on Water. The theme of this event, The Hidden Treasure, Groundwater as a Tool for Climate Adaptation and Resilience, is of particular relevance to the mandate of AMCOW. Our mandate derives from the Africa Water Vision, which is an Africa where there is an equitable and sustainable use and management of water resources for poverty alleviation, socio-economic development, regional cooperation, and environment. AMCOW's role in Africa's efforts to actualize this vision is centered on leveraging political support, mobilizing partnerships, and facilitating the application of knowledge and information to support, first, action to meet water demands for all, that is domestic and small-scale productive water uses. Secondly, action to ensure availability of water for economic production, particularly in the industry, energy, and agriculture sectors. Third, action to reduce disaster risks from such water-related hazards as floods, droughts, and pollution. And finally, to enhance climate resilience. Groundwater's value is underscored by its extensive utilization in the rural economy, which accounts for an average of 16% of GDP in sub-Saharan Africa. Moreover, groundwater utilization has major implications for eradicating poverty and ending hunger. Groundwater access infrastructure range from naturally occurring springs and hand-dug wells to boreholes. In countries like Ethiopia, for instance, at least 70% of domestic water needs are met from groundwater supplies. It is also anticipated that groundwater use in commercial agriculture will rise to meet the dietary requirements associated with urbanization and improved standards of living. In the arid and semi-arid parts of the continent, groundwater resources provide the buffer and lifeline to combat recurrent drought conditions. It therefore goes without saying that functional groundwater infrastructure is essential for resilience. In addition, well-functioning monitoring, assessment, and management systems are required to ensure sustainable use of the resource. In particular, authoritative information on resource potential, recharge rates, ecosystems, and human dependence and utilization is required to ensure sustainable availability of groundwater to meet growing demands under a changing climate. Available information indicates that concerted effort by member states is providing an enabling environment to regulate and manage groundwater resources. While progress is being made, the functionality of these enabling environments and systems are constrained by institutional and technical capacity challenges. These challenges include gaps in legal and regulatory frameworks, fragmented organizational responsibilities, ad hoc resource development, and inadequate funding to provide the equipment and skills required to reasonably assess, monitor, manage, and develop the resources. AMCOW's Pan-African Groundwater Program is addressing these challenges through coordinating, strengthening, and guiding interventions. Through the program, we are collaborating with the International Water Management Institute, the British Geological Survey, and the German Institute for Geosciences and Natural Resources to support member states. It would be amiss of me not to highlight the high hopes we have of the Pan-African Groundwater Program to contribute first to the COVID-19 response, restoration of economic growth, and prevention of future pandemics. And secondly, building resilience of African communities, ecosystems, and economies to climate change and securing a resilient socio-economic transformation. As I conclude, allow me to express our gratitude to the event organizers and the various partners, contributors, and stakeholders that have made this event possible. The agenda and list of discussants are testament to the intent to have an exciting and informative event. As a collaborating partner, AMCOW has high expectations from this engagement to mobilize partnerships to action to raise the profile of groundwater as a key tool for climate adaptation and resilience. On this note, and on behalf of the convener and co-conveners, I welcome you all and wish you all fruitful deliberations. Thank you.
Welcome to COP26 and this session on groundwater. You may not know it, but groundwater supplies 98% of the available fresh water on the planet. When it's not raining, it's groundwater that actually keeps these rivers flowing. And importantly, groundwater is connected to wetlands, an important habitat for biodiversity and for the management of floodwaters.
Land, water, and biodiversity go together hand in hand, and in between them, there is invisible resource, which is the groundwater, which feeds the systems. If we look at adaptation to climate change, what we're finding is that almost invariably, all aquatic systems have a linkage to groundwater. Some are linked to major inflow from groundwater, some minor. And if you look at the average annual flows of most of the rivers in the world, 30% of the flow in the rivers is through the discharge of aquifers into these rivers. So they're pretty fundamental. There are some people who are engaged, some people who are involved, and some people who are aware. The ministers who are attending the conference are there to discuss emissions. While the emissions are very important, the problem that we have to face is adaptation. Land, water, biodiversity. What is the source that will provide the water at times of stress? It's groundwater. So ministers, in addition to looking at emissions, what is your adaptation plan for tomorrow?
Thank you to the distinguished delegates for opening this event. My name is Karen Wilholt. I'm a principal researcher with IWMI, the International Water Management Institute, and I'll be moderating the remaining part of this event. We will have a series of short presentations, which will be followed by a panel discussion where I will be asking questions and we'll have a debate around the various presentations. First, we will have a video which describes what groundwater is, and that will lay the foundation for the subsequent presentations.
What is groundwater, and why is it vulnerable? Most groundwater originates from precipitation that infiltrates into the underground, where it is stored in geologic formations called aquifers. Aquifers come in all sizes, from a few square kilometers to crossing borders of countries. Only a finite amount of groundwater can be stored in an aquifer. Globally, around 2.5 billion people rely on water supplied from underground aquifers as their main source of fresh water. Groundwater is also used for farming, especially during times of drought. Industry uses groundwater when surface water, like rivers, are not readily available or too polluted for production. Groundwater is typically extracted from an aquifer via shallow dug wells or deeper boreholes. Powerful electrical pumps can pump thousands of liters per minute from a single well. When groundwater is pumped faster than it is replenished by precipitation, the water level in a well declines. Groundwater stored in aquifers can be contaminated from the surface. Pollutants dissolved in surface water or precipitation can infiltrate and reach the groundwater. Pollutants released near a well are drawn to it and eventually get pumped to the surface. Therefore, the area around a well must be protected from pollution. Groundwater can be found very close to the surface or at great depth. A shallow groundwater reservoir is much more vulnerable than groundwater protected by thick layers of sediment or rock. Some pollutants occur naturally, such as fluoride, arsenic, or elevated salt concentrations derived from the surrounding rock mass. Groundwater contaminants can be both biological or chemical in origin. Human activities have polluted groundwater with excrement that contains disease-causing bacteria. Agricultural contaminants include pesticides, or excess fertilizer. And examples of industrial pollutants are gasoline, solvents, heavy metals, and pharmaceuticals. Many of the most toxic pollutants are man-made. Once these pollutants enter the groundwater, they require a long time and much money to remove. Many water contaminants can neither be tasted nor seen. Chemical methods are required to test for this water pollution. An estimated 1.8 billion people are using a source of drinking water that is contaminated by fecal matter or bacteria. Access to safe drinking water is one of the most challenging problems of the 21st century. The potential of groundwater pollution increases with the number of people living close together. That is, an aquifer underlying urban areas with a high population density and industry is more likely to be polluted compared to groundwater reservoirs in more rural areas. However, in rural areas, wastewater is often not treated, and therefore can contaminate the local groundwater with bacteria and agricultural pollutants. Populations that live near the coast often pump more water than is replenished naturally. This can lead to the intrusion of salt water into coastal aquifers. Once salt water pollutes an aquifer, the well must be shut down. Every person has it in their control to protect local groundwater from pollution at the community level, by educating oneself about groundwater issues. A couple small examples include providing access to plumbed toilets rather than outdoor latrines, disposing toxic household products appropriately, and avoid using toxic products or packaging whenever possible. Farmers should only apply the minimum amounts of fertilizers and pesticides needed. Industry should follow less toxic or non-toxic alternatives in their production process. When building a new home, install an on-site wastewater treatment system to clean domestic water before it seeps back into the ground, and talk to your neighbors and friends about protecting their wells as well. Become involved in your community. Put pressure on local industries and regulators supervising them, and demand that environmental laws are being followed. This is what we can do to protect our groundwater and the groundwater for the future generations to come.
Nice video. Thanks for that. Now we will move into something a little more practical, and we will be hearing from Skip Bacchus, who is the CEO of the Omega Institute in the US, and he will be speaking to us about their experiences from implementing nature-based solutions based on groundwater. Over to you, Skip.
Hello, my name is Skip Bacchus. I'm CEO here at Omega Institute in Rhinebeck, New York, and I'm standing in front of Long Pond Lake, which is one of 3 lakes that really act as recharge for the aquifer in this section of Dutchess County. With Long Pond Lake as a backdrop, we steward about 250 acres here in Rhinebeck. So when we were thinking about what does it mean to be a steward of this land, water usage became a premium topic, a major issue for us. So the first thing that we had to do was to really come to grips with how much water do we use, how do we use it, how can we use less, and then how do we better fit into a complete hydrological cycle so that our impact is as minimum as possible. So coming in to the building from down below, that's my favorite shot of the building from down there on the southern facade, where you can see the solar panels that power this building and the constructed wetlands part of the waste purification. But the way that this actually works is we had to take a deep look at how we dealt with wastewater. Not only from the standpoint of wanting to have a neutral stance with our overall utilization of water in terms of a closed hydrological loop, but what are the opportunities as Omega, again being an education institute, how to teach people about just the preciousness and the processes that are involved with water. So we came up with the help of many different engineers, what's called an eco machine, which is basically nature's way of purifying water with plants and microorganisms. No chemicals and no energy because we power it with the solar panels. So now what happens on campus is we pull the water out of the ground from our deep wells, some of them 250, 300 feet deep. We send it up to the top of the hill, a change in elevation of about 300 feet to create water pressure, and then utilize it on campus for everything, toilets, showers, food prep. 100% of the water now, as it's used, comes down here for purification. And that process itself is very simple. It's through a series of equalization tanks, anoxic tanks, constructed wetlands, aerated lagoons, sand filters, and then the magic is we put it out into a series of infiltration beds that we've built that trickle it back down into the aquifer and recharge the aquifer. So we've pulled the water out of the aquifer, utilized it, purified it, put it back. Managed aquifer recharge here at Omega. So we are basically in a neutral position with our water usage on campus. So after 12 years of running this eco machine, and I'm not sure if we're running it or it's running us at this point, but over 60 to 70 million gallons of water have been purified and been used and recharged the aquifer. And we run very many tours through this building as well. And one of the things that I'm always surprised by is that people don't realize where their water comes from. So one of the primary pieces we're trying to do with this facility, the Omega Center for Sustainable Living, is to really be able to educate people to that you must be in relationship with your water. Where does it come from? How do I use it? What is my impact? And that's my hope for as we look to dealing with a lot of the serious challenges that we have with climate, that a little piece of the puzzle can come together through institutions really looking at how they live with their water.
Thank you, Skip, for this nice presentation. We will now be moving to Africa, and we will be hearing from Bob Kaelin. He is a professor at the University of Strathclyde in Scotland, and he is probably in the pavilion at this point in time, so some of you might be able to meet him in person. He will be speaking about the work that he has been doing in Malawi over many years, looking at the groundwater conditions and the links to water security and resilience. Over to you, Bob.
Hi, I'm Professor Bob Kaelin of the University of Strathclyde. Welcome to COP26 and this session on groundwater. We provide here an example in Malawi where groundwater resources play an important role for the people of Malawi, for their ecosystems, and importantly for the water, food, energy nexus. Without groundwater management, the adaptation to climate change will be a huge challenge.
With climate change, we have had droughts, and then there's groundwater depletion in the on the ground surface, and we are kind of like now being forced to go into looking at deeper aquifers.
Malawi is a country in sub-Saharan Africa with a population of over 18 million people, 85% of which are dependent upon groundwater. It has two seasons, a rainy wet season from November until the end of March, and a dry season from April until the end of October. Lake Malawi is a substantial surface water supply, and even though the population depends upon groundwater, it wasn't until a recent national audit of all rural water points that more was known about groundwater as a resource.
Activity itself was done on the ground, reaching out to each and every water point, either improved or unimproved, but it was all mapped, and then sanitation facilities were also mapped together so that we can see the difference, to make the near proximity between the two.
Substantial data was collected on over 100,000 water points to evaluate their functionality, their management, and the resource sustainability.
The issues of data goes a long way in making that we are planning well, because you can't plan if you don't know how much resources you have, how much facilities are there, in what state. So the data that is there is assisting so much in planning.
We were surprised to find how critical annual groundwater table variations were. Over 17,000 rural water supplies did not provide adequate water at the end of the dry season. And detailed data shows annual and ENSO variations in groundwater levels with a long-term trend in water table decline. And this is important because it's groundwater that provides the water flowing in the rivers during the dry season and when it's not raining. Study of the groundwater surface water link found that across Malawi, groundwater accounts for more than 50% of river flow, and for some catchments over 90% during the dry season. Given many of these rivers feed Lake Malawi or are transboundary, groundwater storage capacity is of national and international importance. The end results suggest groundwater is the resilient resource. It provides water to wetlands and rivers, which in turn provide water to Lake Malawi. Groundwater storage buffers the annual wet and dry seasonal changes, as well as climate variation and the effects of climate change. The management of groundwater resources in the face of deforestation, land use change, and increasing climate variability must be a priority, as it also supports energy security. Water from Lake Malawi flows out the Shiri and provides most of the hydroelectric power in Malawi.
It has also changed the amounts of water that we want, because with floods and then the droughts, we have to the people have to change a lot of things, maybe the type of food that they are now supposed to be having, or maybe the type of crops they are supposed to be growing.
And planning is underway for substantial investments in irrigation infrastructure and agriculture for food security. The success of these interventions will be dependent upon well-managed groundwater resources. This highlights a need for science-based policy revision to support Malawi's Vision 2063.
Revising of the national water policy. We have engaged the academia, we have engaged the NGOs, we have engaged many other relevant stakeholders for their input. By the end of the day, we are trying to come up with the facilities and structures which are resilient to these shocks. But at the same time, make sure that we are making available water resources for the country without depleting the environment for the sake of future generations.
Thank you, Bob. And now we'll move to Asia. More specifically, we'll move to Vietnam, and we will be hearing from Dr. Nam from the University of Kanto. He will be speaking about the work that they've been involved in terms of understanding and modeling groundwater resources in the Mekong Delta. Over to you, Dr. Nam.
Bước vào mùa khô, nước ngọt cho sinh hoạt, sản xuất đang dần trở nên khan hiếm. Nước ngầm là nguồn nước ngọt chủ yếu để người dân ở nhiều tỉnh ven biển đồng bằng sông Cửu Long sử dụng. Tuy nhiên, nguồn nước này đang bị khai thác quá mức. Vấn đề đặt ra là phải quản lý nước ngầm ở đồng bằng sông Cửu Long để nguồn tài nguyên quý giá này phát huy đúng giá trị mà thiên nhiên đã ban tặng cho chúng ta.
Thực trạng sử dụng nước đất của đồng bằng sông Cửu Long chúng ta thì nó đang là ngày càng gia tăng. Từ sau năm 2000, tức là bắt đầu là cái nguồn nước ngọt chúng ta suy giảm về chất lượng và cũng như là số lượng. Thì khi đó thì là các vùng như là ven biển của đồng bằng sông Cửu Long chúng ta là sử dụng rất nhiều cái nguồn tài nguyên này. Cái trữ lượng của đồng bằng sông Cửu Long thì hiện tại giờ có nhiều nghiên cứu đã xác định là nó càng ngày càng giảm.
Trong điều kiện khô hạn, nguồn nước ngầm có thể giải quyết được bài toán cân khác về nước sinh hoạt tại đồng bằng sông Cửu Long, nhưng phải phân bổ và sử dụng nguồn nước làm sao cho hợp lý. Thực tế hiện nay, tình trạng người dân khoan giếng một cách tự phát, không chỉ mục đích lấy nước sinh hoạt mà lấy nước để nuôi tôm, kinh doanh dịch vụ, sản xuất công nghiệp đang ngày càng phổ biến, đã khiến nguồn nước ngầm bị suy giảm trầm trọng. Việc quản lý khai thác nước ngầm còn gặp nhiều khó khăn. Hiện nay, đồng bằng sông Cửu Long chưa có quy hoạch khai thác sử dụng và bảo vệ tài nguyên nước. Nước ngầm là tài nguyên chiến lược nên cần có định hướng quy hoạch khai thác tổng thể, không thể mạnh ai người nấy làm như hiện nay. Khai thác quá mức thì đến một lúc nào đó, cấu trúc và tổng thể về nước ngầm của toàn vùng đồng bằng sông Cửu Long sẽ bị phá vỡ. Gần đây, tại nhiều nơi đã có hiện tượng người dân bơm nước ngầm lên yếu hoặc không có nước. Nhu cầu nước ngọt để trồng trọt đã vượt xa mức khai thác an toàn hàng ngày. Điều này sẽ ảnh hưởng rất lớn đến hoạt động sản xuất nông nghiệp của bà con nông dân. Tiến sĩ Nguyễn Đình Giang Nam cùng nhiều cộng sự đang theo dõi, thu thập dữ liệu để tính toán trữ lượng nước ngầm của tỉnh Sóc Trăng cho biết đã có nhiều tác động tiêu cực cho sản xuất nông nghiệp do khai thác nước ngầm quá mức.
Our group in Kanto University used the modeling tool for sustainable groundwater utilization in the Mekong Delta. We use iSmart, which developed by cooperating between the Dentalrest in New Zealand and Kanto University. At first, we developed the regional model for whole Mekong Delta. And then we setting up the downscaling model to answer two questions. How's impact of groundwater pumping and water utilization under climate change? The modeling were used to analyze the impact of groundwater pumping in the urban area of the Mekong Delta. By the modeling tool, the simulation result can help the local government understand how is the groundwater resource under the groundwater pumping scenarios in the urban area. Another model application for the groundwater management measure were developed to look at how is groundwater using in the climate change condition in the Mekong Delta. Due to the freshwater shortage and the soil intrusion caused by the climate change condition in the Mekong Delta, it will make clear that the groundwater resources will be the hidden treasure for the water supply in the climate change condition. Finally, the groundwater model, which has made alternative simulation, result in visualization and easy ways to support the sustainable groundwater utilization and management for the local government in context of climate change condition in the Mekong Delta region.
Thank you, Dr. Nam. Now I'm pleased to hand over to Renee Martin-Nagle, who is the treasurer at IWRA. She will be speaking about offshore aquifers and how that can be a potential solution to resilience in the future. Over to you, Renee.
Hello, my name is Renee Martin-Nagle, and it's my great pleasure to tell you about offshore freshened groundwater, a resource that is lying embedded in continental shelves all around the world and that has not yet been tapped. Due to financial constraints that have limited research and exploration, we're not sure of the exact quantities or locations, but we are sure that the freshest water is close to shore. For that reason, it's easy to envision a time when climate change will force nations to tap offshore resources to address water resiliency. Here's a short video that will tell you more about offshore freshened groundwater, and many thanks to Marcan and Dr. Aaron Mikaloff for making the video available.
When we think of fresh water, images of rivers, lakes, and glaciers usually come to mind. Yet fresh water is also found in sediments and rocks below the seafloor. This is known as offshore freshened groundwater. Globally, offshore freshened groundwater has a total estimated volume equivalent to that of the Black Sea. Recently, scientists from the Marcan project, funded by the European Research Council, discovered a freshened groundwater system offshore the Canterbury coast in the South Island of New Zealand. By integrating seismic reflection profiling and electromagnetic surveying techniques, which allow the identification of geological structures and electrically resistive bodies below the seafloor, the team was able to map the structure of the offshore groundwater system in 3D. This system could host up to 200 cubic kilometers of fresh water and coarse sediments in waters less than 100 meters deep. The fresh water was derived from precipitation and was largely deposited during the last ice age when sea level was more than 100 meters lower than today. But why does this matter? As our freshwater sources continue to deplete, understanding how offshore freshened groundwater can be used as a sustainable source of potable water, particularly in coastal regions and island nations prone to droughts, is very important. So is the identification of its possible applications in seafloor engineering, carbon capture, and resource exploration. The Marcan project's approach can significantly improve assessments of offshore freshened groundwater resources and ensure their sustainable use. To dive deeper into the subject, visit markhand.eu.
The video highlighted several regions where offshore freshened groundwater has been identified, and the map in the upper left corner of this slide shows more precisely the locations where reserves have been confirmed. The video estimated the total volume of offshore freshened groundwater to be equal to the volume of the Black Sea, which holds 500,000 cubic meters. However, some scientists have estimated that offshore freshwater deposits could exceed 1 million cubic meters. Additional funding for exploration would help to clarify the actual volumes and locations. The map in the lower right corner illustrates where water scarcity is projected to occur by 2040. A comparison of the two maps shows that a number of offshore freshwater deposits are lying in coastal areas that may well need to supplement their supplies in the not-too-distant future. When development of offshore fresh groundwater begins, a myriad of legal issues will arise, due in large part to the overlapping governance regimes that may apply. The shoreline marks the boundary between land-based laws and maritime laws, and the Global UN Convention on the Law of the Sea, whose application begins at the shoreline, grants coastal nations exclusive sovereign rights over natural resources for a distance of 200 nautical miles from their respective low tide lines. Some offshore freshwater deposits will straddle maritime boundaries, and rights to those transboundary resources must be negotiated by the relevant parties. Determination of ownership rights is just the beginning of the legal analysis, though. The Global Convention on Biological Diversity and the various regional seas agreements contain provisions regarding environmental protection that would impact both exploration and extraction of offshore fresh water. And the ESPO agreement, which applies to most European countries, requires environmental impact assessments early in natural resource development. Access to offshore aquifers connected to land-based groundwater may trigger application of the Ramsar Convention for protection of wetlands, and coastal management laws and regulations will determine how and by whom offshore freshwater is developed. In addition, legal principles for land-based freshwater may influence how the resource is allocated and utilized. The tangle of global, regional, national, and local laws presents opportunities for collaborative, holistic action among a variety of stakeholders. Thank you for your attention, and I hope that you have been inspired to learn more about offshore fresh water, which may play a significant role in ensuring resiliency to climate change.